In this short video, now I would like to give a simple illustration on how we derive the straight line sketching for a slightly complex system. This is the system that we are going to consider, where the Bode diagram is going to be sketched. We have a system where the transfer function is equal to 10s plus 3 divided by s squared plus s plus 2. Just as a side story, this transfer function is coming from two transfer functions connected in serial connection, GS and HS. If you want to have to plot it with your computer, then what you have to do, you just simply have to convert it to frequency domain by substitute j omega to all of the s's, find the magnitude, convert it to dB scale, find the phase accordingly, and then plot the magnitude in dB scale and phase in linear scale as a function of frequency in logarithmic scale. But what we are going to illustrate now in this short video is how to sketch it with a straight line approach by what I'm going to do now. I will factorize this transfer function into 4 terms like this. The reason why I split it into these 4 terms, because each of these 4 terms is represented by the simple transfer function that we have already discussed in the previous video. So as you can see here, the first term basically here is a static system that corresponds to the first simple system in the previous video, GS equal to A. In our case here, A will be 15. The second term here basically is the integrator. The third term here basically is the inverse of first order system, and the last term here is simply a second order system. So having the Bode diagrams of these individual 4 simple systems, we should be able later on to illustrate the Bode diagram for this complex system. The Bode diagrams for each of these 4 simple systems will be like this. This will be the Bode diagram for the first simple system, where it is just simply a constant transfer function here, where the constant here is equal to 15. This corresponds to the first simple system in the previous video, where A now is equal to 15. For the magnitude plot, we will have constant of 20 log 15 all over frequency, where for the phase we will have 0 degrees for all frequencies. The second simple system is the integrator, where the magnitude plot is just a straight line with a slope of negative 20 dB per decade crossing the origin here, and the phase plot is just simply equal to negative 90 degrees for all over frequency. The third simple system is the inverse of first order system. The corner frequency is at 3, 0 dB at low frequency, positive 20 dB per decade at high frequency beyond the corner frequency of 3. For the phase, we have 0 degree at low frequency and positive 90 degrees at high frequency. For the fourth simple system, we have a second order system here. The corner frequency is the omega n, so it will be equal to square root of 2 for the corner frequency, or it will be equal to 1.414 radian per second. The magnitude plot will be 0 at low frequency region, and it will be aligned with negative 40 dB per decade at high frequency region beyond 1.414 radian per second. As for the phase, we will have 0 degree at low frequency, negative 180 degrees at high frequency beyond the 1 decade above the corner frequency. So for this phase plot, I will take the approach of the 3 region phase plots that we have already discussed before. Having all of the magnitude and phase plots for 4 simpler systems, we can now reconstruct the magnitude and the phase plots for the complex system. I will start it first with the magnitude plot. I will plot it again here for the 4 simple systems. This is the magnitude plot for G1, magnitude plot for G2, for G3, and for G4. Having all of these magnitude plots for the 4 simple systems, the magnitude plot for the complex system will be just the superposition of these all 4 magnitude plots. But now I will superpose all of these plots separately. I will split it into different regions. I will start it for the low frequency until the first corner frequency at 1.414 radian per second. If you look at this, I will have constant line because of the G1 for the magnitude plot, where the line here is equal to, the value is equal to 20 log 50. From G2 I will have a negative 20 dB per decade slope crossing the origin. From G3 I will have 0 dB line, as well as from G4 I will have 0 dB line. So from low frequency until 1.414 radian per second, I will just simply have to sum 20 log 15 plus the line of negative 20 dB per decade from G2, because for G3 and G4 I will have 0 dB line. After I sum these 2 plots, this is what I will get. At the low frequency region below the first corner frequency, I will have negative 20 dB per decade line shifted up by 20 log 15. And then between the first corner frequency and the second corner frequency, if you look at this, from G1 I have 0 slope. From G2 I have negative 20 dB per decade slope. From G3 I will have 0 slope as well, and from G4 I will have negative 40 dB per decade slope. Therefore, within this region, between the first corner frequency and second corner frequency, I will have negative 20 dB per decade slope plus negative 40 dB per decade slope. Therefore, between these 2 corner frequency, I will have negative 60 dB per decade slope. And now, beyond the second corner frequency, I will have 0 dB per decade slope from G1. I will have negative 20 dB per decade slope from G2, positive 20 dB per decade slope from G3, and negative 40 dB per decade slope from G4. So these 2 from G2 and G3, they will cancel each other. Therefore, at the end, beyond the second corner frequency, beyond 3 radian per second, I will have negative 40 dB per decade slope line. So this, the black line here, illustrate the straight line approximation of the magnitude of our complex system. What about the phase plot? It will be the same. I will plot the phase plots of all of the 4 simple system. This will be for G1, this is from G2, this is the phase plot, the green one is the phase plot from G3, the yellow dash line is the phase plot from G4. Of course, now here I will have more regions to consider. At low frequency region until 1 decade below the first corner frequency. So 1 decade below the first corner frequency will be 0.1414. What I will get in here, I will have 0 degree from G1, and then I will have negative 90 degrees from G2. I will also have 0 degrees from G3, I also have 0 degree from G4. Therefore, if I superpose all of these 4 phase plots at low frequency region until 1 decade below the first corner frequency, or until 0.1414 radian per second, I will have negative 90 degrees line. And from 1 decade below the first corner frequency, 0.1414 here, until 1 decade below the second corner frequency, or 0.3 radian per second, I will have 0 slope, right? 0 slope as well from G2, right? And then I will have negative 90 dB per decade slope from G4. I will have 0 slope from G3, right? So within this region, I will have negative 90 degrees per decade slope. What will happen from 0.3, 1 decade below the second corner frequency, until 1 decade above the first corner frequency? If we look at this, I will have 0 slope from G1. I will have also 0 slope from G2. I will have positive 45 degrees per decade from G3 and negative 90 degrees per decade slope from G4. Therefore, from 0.3 until 14.14, I will have negative 45 degrees per decade slope. And then I will have the third region from 1 decade above the first corner frequency until 1 decade above the second corner frequency. Let's take a look again here. 0 slope from G1, 0 slope from G2, positive 45 degrees per decade from G3, and then 0 slope from G4. Therefore, within this region, I will have positive 45 degrees per decade slope. And then beyond 1 decade above the second corner frequency, I will just simply have 0 slope from G1, 0 from G2, 0 slope from G3, as well as 0 slope from G4. So this will be the straight line sketching of the phase plot of the complex system, considering the 3 frequency region approach of phase plot sketching. As an alternative, of course, you can also use the 2 region phase plot approach. This will be the alternative when you are using the 2 region phase plot approach. Of course, in here we will have some abrupt jumps accordingly. If blue one here is the straight line sketching of the phase plot for G1, red is for G2, green is for G3, and the yellow one is for G4, then by superpose all of these 4 plots, I will get this straight line approximation for the phase plot. Of course, the result here will look much coarser compared to the previous one, but this is much simpler to sketch. The price, of course, the previous one looks closer to the reality, to the result of the real phase plotting. Okay, so this short video illustrates how we can sketch the magnitude and the phase plots using a straight line sketching methods.